If an AI model is 99% accurate at finding a rare disease, it might actually be completely useless in the real world. Seriously. That impressive 99% number? It could be hiding an absolute catastrophic failure.
Welcome to this explainer. Today, we're bridging the gap between polished machine learning theory and the gritty reality of practical application. We're going to break down how algorithms actually learn, how they correct their mistakes, and most importantly, how we figure out if they're actually doing their jobs safely.
To do this, we're contrasting formal, polished lecture slides from Dr. Nafis Sadek at East West University with a student's actual handwritten notes. Seeing the dense math right next to someone literally trying to make sense of it gives us this brilliant, grounded look into the reality of these algorithms.
So here is our roadmap. 1. Regularization to prevent model overfitting. 2. Optimizing with gradient descent. 3. The imbalanced data trap. And 4. Precision, recall, and F1.
All right, let's jump right into Section 1, Regularization, Preventing Model Overfitting.
First up in our machine learning lifecycle, we've got to establish the mathematical rules that stop our model from just blindly memorizing the training data. Because if a model just memorizes, it's totally lost when it sees new information. To prevent this, we use a really neat mathematical trick. On the left side here, you've got standard cross-entropy loss, which just measures error. But on the right, we add a penalty term, lambda times the L2 norm of our parameters. This is L2 regularization. By penalizing large parameters, we're basically forcing the model to find simple, robust patterns instead of complex, hyper-specific ones that only work on the training data.
And in practice? Well, if those parameter values get too large, the L2 norm balloons and the model starts overfitting. Or, as the student so perfectly phrased it right here in the margins, it starts overthinking. Applying that lambda penalty is essentially the exact mathematical cure for an overthinking algorithm.
Moving right along to Section 2. Optimizing with gradient descent.
This part turns some incredibly complex math into a highly logical step-by-step pipeline. We start by computing a linear score, then we squash it into a probability between 0 and 1 using a sigmoid function, calculate how badly we missed the mark, and then, finally, update our parameters using the gradient.
But the real magic happens in this update rule right here. This is gradient descent. We take our current parameter, theta, and we update it by subtracting the gradient of our loss function multiplied by our learning rate, alpha. Since the gradient points in the direction of steepest descent, meaning the absolute highest error, subtracting it literally forces the model to take a step downhill. It just keeps inching closer and closer to the best possible answer.
And you can actually see this trial and error happening line by line right here. The student multiplies the gradient by a step size of 0.1, subtracts it, and watches the value physically adjust from 2 to 2.4 to 2.72. I mean, it's literally the heartbeat of an algorithm learning from its mistakes.
Which brings us to Section 3, the imbalanced data trap.
Now here is where traditional grading completely falls apart. Imagine a dataset with 100,000 files. 99,000 are clean, and just 1,000 are malicious salvage files. If you build an incredibly lazy AI that just guesses clean every single time, without even looking at the data, it hits 99% accuracy. It completely failed its actual job of finding the malicious files, yet it gets an A+. As the notes bluntly state here, accuracy will not work if the data is imbalanced.
So to fix this trap, we have to throw out basic accuracy entirely and use a confusion matrix. This table forces us to map our correct guesses, our true positives and true negatives, right against our dangerous mistakes, our false positives and false negatives, because out in the real world, all mistakes are definitely not created equal.
Think about it like this. Imagine a model predicting if a tumor is malignant. A false positive, saying a tumor is malignant when it's actually benign, might cause what the student calls patient tension or require extra testing. It's stressful, sure, but manageable. But a false negative, predicting a malignant tumor is perfectly safe, that is a catastrophic life risk problem. Basic accuracy completely ignores the massive difference between a minor inconvenience and a fatal error. And that leads us into our final segment, Section 4, Precision, Recall, and F1.
Since high accuracy can easily hide major failures on minority classes, we need entirely new metrics to grade our models fairly. And this is exactly where precision and recall come in. Precision asks a very specific question.
Out of all the times our model predicted a positive result, how many was it actually right about? It's a measure of quality. Recall, on the other hand, asks, out of all the actual positive cases out there in the real world, how many did our model successfully detect? That one's a measure of quantity. And usually you kind of have to trade one off against the other.
Which brings us to the F1 score, sort of the ultimate problem solver here. It's the harmonic mean of precision and recall. And unlike a regular average, a harmonic mean severely punishes extreme values. If a model has great precision but terrible recall, the F1 score just tanks. It forces the model to balance both types of errors, making it absolutely the perfect evaluation metric when you're dealing with imbalanced datasets.
By utilizing the F1 score, or the balanced error rate, calculated right here by hand, we finally treat both the majority and minority classes equally. We can guarantee that the model actually works for those rare, critical edge cases, and we ensure we don't fall for that totally misleading 99% accuracy trap.
So, I leave you with this final thought. The next time a company or a researcher claims their shiny new model is 99% accurate, well, you now know exactly why that number might be completely meaningless. If they haven't tested it with precision, recall, and the F1 score, are we really trusting our future to models based on a deceptive metric, especially when the stakes are literally life and death?